Physics is a Greek word, and in a wider sense, it means science of nature. All physical phenomena have to be reproducible is one of the vital elements in physics. It is important that all the theories be established by experiments or observations, as it is the initial step towards the progress of any physical theory. The next step would comprise of structuring a model or theory in order to explain the experiment or the observations. Besides producing results of the said theory, a model also has to make predictions. Predictions are important to clearly grasp the model of the physical process. To conclude, the theory needs to be corroborated by the experimentations offered by the model. The model will be accepted and validated only if the forecasts are correct. It is important that more experiments be directed with more precision to test the theory over and over again. In physics, it is said that an experiment might be enough to quash a model, and there are no fixed numbers of experiments which can verify that the theory is absolutely correct. There is dissimilarity among models overall and fundamental concepts. Models are basic descriptions of nature, whereas fundamental theories are sources on some maxims from which, in principle, all physical occurrences can be explained. Like, a complicated system is abridged by justified suppositions. These models play a vital role in nuclear physics, where the collaboration is very complex to permit a usage by first principles. For all situations, it is important that a theorist be imaginative and intuitive, as having a good imagination is more significant than being knowledgeable. It denotes the cognizance of mechanics of how the universe functions. History of physics. The rudiments of what has now become physics were mainly derived from fields like optics, astronomy, and mechanics. These subjects were meticulously unified via the study of geometry. All these mathematical disciplines started in the ancient times with the Babylonians and Greek writers Ptolemy and Archimedes. The ancient beliefs concentrated on explaining the nature through ideas such as the four types of cause by Aristotle. The lucid understanding of nature started in Greece with pre-Socratic philosophers since the Archaic period, which was somewhere around 650 to 480 BCE. It was Thales from Miletus who refused to accept any mythological, supernatural, or religious explanations for the natural events that happen around. Instead, he said that for every event, there was a natural cause. Thales was successful in many progresses and accepted water as the basic element and experimented with various subjects like magnets and rubbing amber to form cosmologies. Thales has been named as the father of science. There were many after Thales like Anaximander, Heraclitus, Leucippus, who challenged each other's theories, and it was Democritus who finally discovered the theory of atomism. His theory said that all the things in the universe were composed of indivisible and imperishable elements known as atoms. This was a milestone in the history of physics and to a much evolved atomic theory of today, as everything revolves around the atoms, their size, state, arrangements, etc. Aristotle had discovered physics in a much detailed way. His writings and works and his student led to the discovery of the laws governing the physical phenomenon. In India, the philosopher Maharishi Kanada was the first to uncover the systematic theory of atomism in 200 BCE, which was further detailed by two Buddhist atomists, Dignaga and Dharmakriti. The theories of Indian philosophers were merely based on logic and void of any experience or experiments, and were therefore considered as non-concrete and entangled. Later, in 499 BCE, astronomer Aryabhata offered the theory of Earth's rotation through his works Aryabhata. Shen Kuo from China has been accredited with the study of magnetism and described the magnetic needle compass. Later on, he developed the camera obscura, device which later led to photography. Ibn Sina, a famous polymath from Uzbekistan, then Bukhara, made many important contributions in the fields of optics, philosophy, physics, and medicine. Ibn al-Haytham is considered as the founders of modern optics. Works of the Muslim scientists like Abu Rayhan Biruni and Ibn al-Haytham traveled to Europe, which was studied by the scholars. The awareness of historical works entered West by translation of Arabic works to Latin. This reintroduction of works was merged with Judeo-Islamic doctrinal explanations, and the medieval European scholars were greatly impressed by these works, as they wanted to reunite the philosophy of the historical theorists with Christian theology. Mechanics. The science which is related with the behavior of bodies when force or displacement is applied, and the consequent effects of these bodies on the surroundings, is known as mechanics. Or we could frame it in an easier way, the science that is concerned with the motion of physical bodies under action of forces, inclusive the time when a body is at rest. This theory further leads to studies of various topics such as electricity, magnetism, and gravitation as per the nature of forces connected. Considering the fact that one can pursue the manner of how the bodies move when these forces are applied, this is actually what mechanics means. Mechanics was the first among the few exact sciences that was developed in the ancient times. The internal beauty of mechanics as a mathematical discipline and its early extraordinary accomplishment in accounting and incomputable facet for the motions of the Earth, of the Moon, and other terrestrial bodies had huge effect on metaphysical thought and gave motivation towards the methodical growth of science into the 20th century. There are three branches which mechanics can be divided in. Statics deals with forces acting in and on a body which is at rest. Kinetics that endeavors to clarify or forecast the motions which will occur in a certain state. Kinematics, which defines the probable motions of a body or structure of bodies. On the other hand, mechanics can be distributed as per the type of system studied. The most simple of all mechanical systems is particle, which can be described as a very small body which does not have any internal structure or shape, and is of no importance in the definite problem. The motion of a system, which has two or more particles which apply forces on each other and perhaps endure forces applied by bodies in the external of the system, this is a more complicated situation. The principles of mechanics are functional with three overall realms of occurrences. The motion of universal bodies like planets, stars, and satellites can be foretold exactly many years before they can happen. The theory of relativity foretells some deviancies from the motion as per the Newtonian or classical mechanics. Nevertheless, these deviations are too small to be observed without proper techniques, excluding problems which involve a big part of the noticeable cosmos. As the second domain, ordinary substances on Earth which are of microscopic size, which move at a speed that is lesser than light, are explained by classical mechanics without important rectifications. An engineer who structures aircraft and bridges might use the Newtonian laws of classical mechanics with assurance, even if the forces seem to be complex and the calculations do not have the minimalism of celestial machines. The behavior of electromagnetic and matter radiation on atomic and subatomic scale encompasses the third realm of phenomena. Even though there have been many achievements earlier against the description of atoms where classical mechanics is concerned, these phenomena are appropriately used in quantum mechanics. Classical mechanics studies the motion of physical bodies under the effect of forces or with the steadiness of physical forms when all forces are stable. The topic may be assumed as the expansion and use of basic suggests first articulated in Philosophiae Naturalis Principia Mathematica by Isaac Newton, also known as Principia. These hypothesizes are known as the Newton's law of motion. It is amazing to know that even though the three laws of Newton, momentum, angular momentum, and conservation of energy, are not deliberated to be essential or precisely correct, they continue to be true in relativity and quantum mechanics. Force in modern physics is not an essential perception anymore, and mass is the only one among the many traits of matter. Angular momentum, energy, and momentum continue to be the center of attraction. The enduring significance of these philosophies, congenital from conventional mechanics, might help to elucidate why this topic preserves such great prominence in science currently. Genesis of mechanics. Nicolaus Copernicus changed the view of people about how they thought of universe in his book De Revolutionibus Orbium Coelestium Libri, 6 books about the revolutions of the heavenly planets. Copernicus mentioned how predicting the position of planets would become much simpler if Sun, instead of Earth, would be taken as the center of the cosmos. There were certain problems with the theory of Copernicus, as he did not explain why the motion was not apparent if Earth was spinning on its axis. Italian scientist Galileo Galilei provided with an answer to this. He experimented with motion of balls on inclined planes and concluded that physical bodies do not require approximate reason to be in motion. As a substitute, a body moving in the horizontal course would incline to stay in motion except something obstructed it. This is why Earth's motion is not ostensible. Everything on Earth and surrounding it are in motion together, which is why they seem to be in rest. Many theories like Galileo, Descartes, Kepler, and others prepared the stage for Newton's impressive synthesis he additionally gave to the world, the theory of universal force of gravity. Newton also published his book Principia, in which he set out his basic hypothesis regarding motion, mass, and force. Wave. A commotion which travels through a medium, mass, or space from one location to the other can be defined as a wave. The motions of wave transfer energy from one point to the other, and this relocates the particles of the mode of transmission, and there is very less or no mass transported. Instead of oscillating or vibrating, waves consist around most of the stable locations. Waves could be distributed in 2 main types. Mechanical waves, which promulgate via medium, the material of the medium is distorted. The distortion backs itself because of the restoring forces, which results from its own distortion. Like sound waves promulgate from air molecules and crash with their neighbors, on colliding, they tend to bounce away from each other, restoring force, and this keeps the molecule going and they continue traveling in the course of the wave. Electromagnetic waves comprise of periodic oscillations of magnetic and electrical fields, which are initially produced by particles which are charged and hence can travel through vacuum. These waves do not need a medium to travel. They have different wavelengths and comprise of microwave, infrared radiation, radio waves, gamma rays, ultraviolet radiations, visible light, and X-rays. Waves can be defined by wave equations, which set out how the disruption ensues over time. The type of the waves decides the mathematical form of the equation. Additionally, the activities of particles in quantum mechanics are termed as waves. The gravitational waves also move through space. It is because of the movement or vibrations caused in the gravitational fields. A wave could either be longitudinal or transverse. Longitudinal waves take place when the oscillations are parallel to the course of energy promulgation. Transverse waves take place when a disruption generates oscillations which are perpendicular to the promulgation of transfer of energy. In free space, all electromagnetic waves are transverse, whereas mechanical waves could either be longitudinal or transverse. There's no single all-inclusive direct definition of wave. A vibration happens when particles of a medium of an elastic body move periodically back and forth, which happens when any physical system is moved from its standing position and permitted to respond to the forces which try to reinstate the equilibrium. Nonetheless, a vibration is not inevitably a wave. An effort to outline the essential and adequate physiognomies which qualify a phenomenon to be named a wave results in an uncertain borderline. Description of waves is associated closely to their physical source for every precise occasion of a wave process. Like the acoustics is differentiated from optics in that sound waves are connected to a mechanical then electromagnetic wave transmission triggered by vibration. Perceptions like elasticity, momentum, inertia, and mass hence become essential in explaining acoustic as discrete from optic wave processes. This difference in origin hosts definite wave facets specific to the properties of the involved medium. For air, pressure, shock waves or vortices. For solids, dispersion or Rayleigh waves, etc. Additional properties frequently defined in terms of derivation might be indiscriminate to all waves because the theory of waves signifies a certain branch of physics which is connected with the properties of wave processes self-sufficiently of their bodily source. For instance, established on mechanical origin of acoustic waves, a moving disruption in space-time can occur only if the medium involved is infinitely pliable and stiff. If all the fragments building up a medium were tightly bound, then they would be vibrating as one without any interruption in the transmission of the vibration and consequently no wave motion. Whereas, if all the fragments were free, there would be no transmission of vibration and once again resulting in no wave motions at all. The above statements would not be valid if waves do not need a medium. They show characteristics which are relevant to all waves irrespective of their origin. The phase of vibration within a wave is distinct for adjacent points in space, as the time taken to reach the adjacent points is disparate for every vibration. Physical properties. There are some common behavior which waves exhibit in certain situations. Transmission and media. Waves usually move in a straight line via transmission medium, and they could be linear medium, bounded medium, isotropic medium, uniform medium, and anisotropic medium. Absorption. Certain waves which strike matter are absorbed by them, transforming them into a vibrational mode. Reflection. On striking a reflective surface, waves change their course so that the angle which is made by the incident wave line normal to the surface is equal to the angle which is made by the wave that is reflected and the same line. Interference. Waves which encounter with one another combine by superposition and create new wave known as interference pattern. Diffraction. On encountering a hurdle which bends the wave is diffraction. Polarization. When a wave motion happens in concurrently two orthogonal directions, it causes polarization. Only transverse waves can be polarized. For example, the electromagnetic waves transmitting in space can be polarized as they are transverse. Sound waves are longitudinal, hence cannot be polarized. Dispersion. The best example of dispersion is when white light passes through a prism which produces a spectrum of colors. Thermodynamics. This section of physics studies the temperature and heat and their relation to work and energy. Thermodynamics describes macroscopic variables like pressure, entropy, and integral energy, which partially define radiation or a body of matter. According to thermodynamics, the actions of those variables depends on the general constrictions which are mutual for all materials beyond the unusual properties of specific things. The macroscopic explanation of processes and bodies can be referred to as thermodynamics in plain terms. Default to equilibrium as contract to non-equilibrium is what denotes the plain term thermodynamics. The competent term statistical thermodynamics denotes the explanation of processes and bodies in terms of the other microscopic constitution of matter or atomic using probable and numerical intellectual. One of the vital concepts in thermodynamics is thermodynamic equilibrium. The most distinctive quantity and well-defined system of thermodynamics is its temperature. The exact study of thermodynamics gets more tough if the processes and systems of curiosity are moved away from the thermodynamics equilibrium. Comparatively easy estimated calculations, still using the variables of equilibrium thermodynamics, are of much applied value. Many essential applied engineering circumstances, as in refrigerators or heat engines, can be estimated as structures containing of many subsystems at diverse pressures and temperatures. If a physical procedure happens very fast, the equilibrium thermodynamic variables like temperature will not be properly set to supply a helpful calculation. There are 4 laws in fundamental types of entities in thermodynamics. However, originally there were 3 laws which have now been classified into 4. The 0th law says that if there are 2 bodies which are in equilibrium with the third body, then they are also in equilibrium with one another. Hence, temperature is established as a fundamental and measurable property of matter. According to the first law, the total rise in the energy of a system is equivalent to the rise in thermal energy and the effort done on the system. This means that heat is a form of energy and is thus subject to the principle of conservation. The second law states that heat energy cannot be transmitted from a body at a lower temperature to a body at a higher temperature without additional energy. Now you know why air conditioners are expensive to run. The third law states that the entropy or waste energy of a crystal at absolute zero is 0. Entropy is at times referred to waste energy, which is the energy that is incapable of doing any work, and as there is no heat energy of any kind at absolute zero, there can be no waste energy. Entropy is also a degree of the disorder in a system, and despite the fact a perfect crystal is by description flawlessly ordered, any positive value of temperature signifies there is motion inside the crystal that leads to disorder. Because of this, there can be no physical system with entropy lower than that. Hence, entropy will always have a positive value. It is important that a physical system's internal atomic mechanism falls into one of the 2 categories for statistical thermodynamics and thermodynamics to apply on it. The atomic mechanism should be so fast that in a given time frame, the atomic states speedily bring system to its self-state of internal thermodynamic equilibrium. The atomic mechanism is so slow that in the given time frame, the system is left unchanged. The fast atomic mechanism is because of the internal energy of the system. They are mediators for the macroscopic alterations which are concerned for statistical thermodynamics and thermodynamics, as they bring the system close to thermodynamic equilibrium in no time. Statistical mechanics and thermodynamics are not applicable if intermediate rates are present, as this rate of atomic processes doesn't bring the system close enough to thermodynamic equilibrium within the given time of the macroscopic process of interest. The separation of time gauges of atomic processes is a theme which repeats all through the subject. Like the traditional thermodynamics is categorized by its study of resources which have or characteristic equations or equations of state. They prompt equilibrium associations among temperature and inner energy and macroscopic mechanical variables. They show the organized individualities of the material of the system. A conventional material can normally be explained by a function which makes pressure reliant on temperature and volume. The pressure which is built is much faster than any enforced modification of temperature or volume. The specifics of thermodynamics could be elucidated by describing objects as assemblies of atomic objects which follow Hamiltonian dynamics. The atomic or microscopic objects occur in species, and the objects of all species being the same. This cause of resemblance and statistical methods could be used to account for the macroscopic characteristics of thermodynamic system as per the characteristics of microscopic species. This description is known as statistical thermodynamics and is at times denoted by the term statistical mechanics, although this term could have a broader meaning, speaking of microscopic objects like economic quantities which do not follow the Hamiltonian dynamics. Electromagnetism. Electromagnetism is a part of physics that covers magnetism and electricity and the interaction with each other. It was first learned about in the 19th century and has been broadly put to use in modern world of physics. The science of electromagnetic fields is fundamentally electromagnetism. A field made by objects which are electrically charged is known as an electromagnetic field. Infrared waves, radio waves, ultraviolet waves, and X-rays are all electromagnetic fields in a particular range of frequency. The occurrence is also known as electromagnetic induction. Likewise, the magnetic field is generated by motion of electric charges. The basic law of electromagnetism is known as Faraday's law of induction. The occurrence of electromagnetism was learned in the 19th century, which helped Albert Einstein in the discovery of the special theory of relativity. According to the theory of Albert Einstein, with the relative motion, magnetic and electric fields can be turned into one another. It was not only Albert Einstein who discovered this phenomenon and its uses, but the works of many amazing scientists like James Clerk Maxwell, Michael Faraday, Heinrich Hertz, and Oliver Heaviside, who contributed to the theory. In the year 1802, a scholar from Italy proved the relationship between magnetism and electricity by refracting a magnetic needle with the help of electrostatic charges. Electromagnetism is merely a speculation of a mutual continence of an unrevealed force called the electromagnetic force. The force is visible when an electric is traveling. The movement caused by the travel generates magnetism. In 1865, James Clerk Maxwell was the first to present this theory to the world through his publishings of electricity and magnetism. Using Maxwell's theory as the foundation, many other scientists discovered the effects and the applications of magnetism. Electromagnetism has been stretched to the area of quantum physics as well, where light interacts as a particle and proliferates as a wave. It has been evidenced that magnetism can give rise to electricity and vice versa. An example to prove is that of an electric transformer. The exchange happens within the transformer, which gives rise to electromagnetic waves. Another datum of these waves is that they do not require a medium to proliferate even though their speed is comparatively more leisure while moving through transparent materials. After the electromagnetic waves had been discovered by James Clerk Maxwell, it was later on established by Heinrich Hertz. Maxwell copied a waveform of magnetic and electric equation which presented that the magnetic and electric fields had the nature of waves. The aspects which make the electromagnetic waves different from one another are the frequency, polarization, and amplitude. Like a laser beam is rational and there is only one frequency in the radiation. There are different kinds of waves which differ in frequencies like radio waves that are at extremely low frequencies, whereas the X-rays and gamma rays both have high frequencies. Electromagnetic waves can proliferate to quite long distances and are unaffected by any hindrances. They could be huge towers or strong walls. The exceptional interaction of magnetism and electricity has helped in many developments in modern science and technology. There are continuous efforts and steps being implemented all over the world to uncover more properties of electromagnetism and how they could be helpful in our everyday work. More types of forces are gravitational forces, weak and strong forces. Combining the electromagnetism with a weak force produces electroweak force. Applications of electromagnetism. There are many uses of electromagnetism in the world of physics and science. The most common application of electromagnetism is its use in motors. There is a switch present in the motor which continuously switches the polarity of the motors outside. The same thing is performed by an electromagnet also. The direction can easily be changed by reversing the current. There is an electromagnet present in the interior of the motor, but the current is controlled in a way that the exterior magnet repels it. The CAT or CAT scan machine is a well-known application for electromagnetism. The machine is used in hospitals to identify disease. Our body has current within, and the stronger the current is, the stronger the magnetic field. With this technology, the machine is able to detect the magnetic fields and identify which part of the body has more electrical activity. Human brain is an intricate pattern of electromagnetic fields. The electrical impulses cause the brain to function, and if two magnetic fields intersect each other, there is intrusion, which is unhealthy for the human brain. Optics. Optics has been often associated with the making of different types of lenses for telescopes, microscopes, or eyeglasses. However, the term optics broadly discusses the study of light's behavior and its interactions with matter. The development of different optical tools impelled the scientists to closely research the behavior of light, which the tools directed. Optics can be broadly categorized into three subfields of research. A. Geometrical optics, which is the study of light as rays. B. Physical optics, which is the study of light as waves. C. Quantum optics, which is the study of light as particles. A. Geometrical optics. Initial optics researchers use geometry to show this view of light. Light is expected to travel long rays, which are line segments that are straight in free space but might alter direction or even bend if it comes in contact with matter. There are two laws which explain about what happens if light comes in contact with surface. Law of reflection, according to which if light comes in contact with a flat surface, the angle of incidence of the ray is equivalent to the angle of reflection. Law of refraction, which states the way in which a light ray alters its path if it crosses a planar boundary from one substance to another. A direct result of this bending of light rays is if something is half immersed in a glass of water, will look like it is bent. The behavior of optical devices like microscopes and telescopes can be ascertained with the help of the laws of reflection and refraction. The paths of various rays can be traced to see their magnification, relative orientation, and how images are formed. B. Physical optics. The study of the wave properties of light can be termed as physical optics and be categorized in three categories. Interference is the capacity of a wave to obstruct with itself, crafting contained areas where the field is consecutively extremely dark and extremely bright. Diffraction is the capacity of the waves to curve around corners and disperse after passing by an aperture. Polarization denotes the characteristics of light connected to the transverse nature. Anyone can determine the wave nature of sound without the use of any scientific tools. For example, in diffraction, if you stand facing your friend's building and he shouts back at you, his shouts will clearly be audible to you because of direct line of sight. The sound waves moderately cover the corners of the building, enabling you to hear your friend. Wave nature of light is not ostensible because of the wavelength of every wave in each case. For sound to be audible, the wavelength ranges from millimeters to 20 meters, whereas for visible light, the wavelength is only 0.00000005 meters, which is very small in comparison to what a human eye can observe. C. Quantum optics. Quantum optics is the part of quantum physics that is involved in the study of interaction of photons with matter. With conclusions from quantum electrodynamics, quantum optics can be interpreted in the form of obliteration and creation of photons explained by the field operators. The approach enables the use of particular arithmetical approaches which are useful in evaluating the behavior of light, though if it represents something that is physically taking place is a point still in debate. The application of quantum optics can be seen in masers and lasers. The light which is emitted from these machines is in rational state, which means the light looks like a sinusoidal wave. These three types of quantum are still being studied in order to better the geometric models so that there's a better overlap with the wave theory of light. Researchers are having continued studies in this field. Engineering and pure science are thoroughly related with physical optics, and the magnitudes of wave of nature of light are still being unfolded, and many optical machines are being built to take the advantage of this wave nature. Quantum optics is an important thing to understand the theory of quantum mechanics, although numerous hypothetical issues like quantum cryptography, quantum computing are being discovered. Special relativity. Special relativity, also referred to as special theory of relativity in physics, is a commonly recognized and experimentally established physical theory about the connection between time and space. According to Albert Einstein's academic treatment, it is based on two hypotheses. The laws of physics are invariant, which is identical in all inertial. The speed of light in vacuum is same for all those who observe, irrespective of the motion of the source of light. The laws were initially suggested by Albert Einstein, that was published in 1905 in paper on the electrodynamics of moving bodies. The discrepancy of Maxwell's equations of electromagnetism with Newtonian mechanics and the absence of investigational validation for a theorized luminiferous ether is what caused the progress of special relativity. That amends mechanics to take care of situations which involve motions which is nearing the speed of light. Today, special relativity is a precise model of motion at any given speed. Even if the model of Newtonian's mechanics continues to be useful, as it is precise and simple, approximately at minor velocities relative to the speed of light. Special relativity suggests a broad range of magnitudes which have been experimentally proved, including time dilation, length contraction, relativity of simultaneity, universal speed limit, and mass energy equivalence. It has taken the place of conservative belief of a complete universal time with the idea of a time which depends on reference frame and spatial position. Instead of an invariant time gap between two events, there is an invariant space-time interval. If combined with other laws of physics, there are two assumptions of special relativity, which foretell the equivalence of energy and mass, which is conveyed in the energy-mass equivalence formula, E is equals to mc squared, c being the speed of light in vacuum. An important aspect of special relativity is that the Galilean transformations of Newtonian mechanics have taken the place of Lorentz transformations. There cannot be a definition for space and time if they are separated from each other. In fact, space and time are intertwined in a single continuum, which is referred to as a space-time. Events which occur at the same time for a particular observer may happen at different times for a different observer. This is a special theory and implies especially when the curvature of space-time is negligible because of gravity. Albert Einstein framed general relativity in 1915. Disagreeing certain outdated descriptions, special relativity has the ability of managing accelerated frames of references. Today, Galilean relativity is reflected an estimate of special relativity which is effective for low speeds. Special relativity is reflected as estimate of general relativity, which is effective for gravitational fields in conditions of free fall and a very small scale. While general relativity includes non-Euclidean geometry, so as to characterize the gravitational effects as the geometric curvature of space-time, special relativity is contained to the flat space-time referred to as Minkowski space. A closed by Lorentz invariant frame which stands by special relativity can be described at small gauges even in curved space-time. Earlier, Galileo Galilei has already hypothesized that there is no definite and complete state of rest through a principle which is known as Galileo's principle of relativity. Albert Einstein stretched this principle so that it took into account the speed of light, an occurrence that had been recently uncovered in the Michelson-Morley experiment. He also hypothesized that it is applicable for all the laws of physics, inclusive the two laws of electrodynamics and mechanics. Although the fundamentals of physics might not be quite understood by everyone, but it is something which is unknowingly used in our daily life. No matter how hard the subject may be to learn, but it helps us make our lives easy. It plays an important role in the history of mankind and will continue to hold a pivotal place in futuristic science and technology. For those who admire the subject, physics can be an intellectual experience and when studied deeper will never stop to amaze. It is the most basic amongst all the sciences, and other sciences like chemistry, biology, geology or cosmology can be understood by the theories which have been developed in physics. Most of the tools on which the progress of technology and science are dependent have been produced by physics. The presence of physics can be felt all around you, from checking your blood pressure to getting an X-ray done, from petrol required to run your vehicle to electricity at your home, from an email that you send from your computer or laptop to a smartphone that you love to flash, from an airplane to a ship, from a DVD to a television, and even the house that you live in is built with the help of physics. A country's development highly depends on how strong the nation's team of physics researchers or institutes are. Nations understand the importance of physics, and which is why they encourage researches which in turn help in overall development of the country. Understanding physics is important and easy. And fundamental concepts. Models are basic descriptions of nature, whereas fundamental theories are sources on some maxims from which in principle all physical occurrences can be explained, like a complicated system is a bridge by justified suppositions. These models play a vital role in nuclear physics, where the collaboration is very complex to permit a usage by first principles. For all situations, it is important that a theorist be imaginative and intuitive, as having a good imagination is more significant than being knowledgeable. It denotes the cognizance of mechanics of how the universe functions. History of physics. The rudiments of what has now become physics were mainly derived from fields like optics, astronomy, and mechanics. These subjects were meticulously unified via the study of geometry. All these mathematical disciplines started in the ancient times with the Babylonians and Greek writers Ptolemy and Archimedes. The ancient beliefs concentrated on explaining the nature through ideas such as the four types of cause by Aristotle. The lucid understanding of nature started in Greece with pre-Socratic philosophers, since the archaic period, which physics is a Greek word, and in a wider sense, it means science of nature. All physical phenomena have to be reproducible is one of the vital elements in physics. It is important that all the theories be established by experiments or observations, as it is the initial step towards the progress of any physical theory. The next step would comprise of structuring a model or theory in order to explain the experiment or the observations. Besides producing results of the said theory, a model also has to make predictions. Predictions are important to clearly grasp the model of the physical process. To conclude, the theory needs to be corroborated by the experimentations offered by the model. The model will be accepted and validated only if the forecasts are correct. It is important that more experiments be directed with more precision to test the theory over and over again. In physics, it is said that an experiment might be enough to quash a model, and there are no fixed numbers of experiments which can verify that the theory is absolutely correct. There is dissimilarity among models overall to somewhere around 650 to 480 BCE. It was Thales from Miletus who refused to accept any mythological, supernatural, or religious explanations for the natural events that happen around. Instead, he said that for every event, there was a natural cause. Thales was successful in many progresses and accepted water as the basic element and experimented with various subjects like magnets and rubbing amber to form cosmologies. Thales has been named as the father of science. There were many after Thales like Anaximander, Heraclitus, Leucippus, who challenged each other's theories, and it was Democritus who finally discovered the theory of atomism. His theory said that all the things in the universe were composed of indivisible and imperishable elements known as atoms. This was a milestone in the history of physics and to a much evolved atomic theory of today, as everything revolves around the atoms, their size, state, arrangements, etc. Aristotle had discovered physics in a much detailed way. His writings and works and his student led to the discovery of the laws governing the physical phenomenon. In India, the philosophers with Judeo-Islamic doctrinal explanations and the medieval European scholars were greatly impressed by these works, as they wanted to reunite the philosophy of the historical theorists with Christian theology. Mechanics. The science which is related with the behavior of bodies when force or displacement is applied and the consequent effects of these bodies on the surroundings is known as mechanics. Or we could frame it in an easier way, the science that is concerned with the motion of physical bodies under action of forces, inclusive the time when a body is at rest. This theory further leads to studies of various topics such as electricity, magnetism, and gravitation as per the nature of forces connected. Considering the fact that one can pursue the manner of how the bodies move when these forces are applied, this is actually what mechanics means. Mechanics was the first among the few exact sciences that was developed in the ancient times. The internal beauty of mechanics as a mathematical discipline and its early extraordinary accomplishment in accounting and incomputable facet for the motions of the earth, of the moon, and other terrestrial bodies had huge effect on metaphysical thought and gave Maharishi Kanada was the first to uncover the systematic theory of atomism in 200 BCE, which was further detailed by two Buddhist atomists, Dignaga and Dharmakriti. The theories of Indian philosophers were merely based on logic and void of any experience or experiments, and were therefore considered as non-concrete and entangled. Later, in 499 BCE, astronomer Aryabhata offered the theory of Earth's rotation through his works Aryabhata. Shen Kuo from China has been accredited with the study of magnetism and described the magnetic needle compass. Later on, he developed the camera obscura, device which later led to photography. Ibn Sina, a famous polymath from Uzbekistan, then Bukhara, made many important contributions in the fields of optics, philosophy, physics, and medicine. Ibn al-Haytham is considered as the founders of modern optics. Works of the Muslim scientists like Abu Rayhan Biruni and Ibn al-Haytham traveled to Europe, which was studied by the scholars. The awareness of historical works entered West by translation of Arabic works to Latin. This reintroduction of works was merged